So today we're going to be talking about the difference between elements and compounds. An element is the simplest form of matter that has a unique set of properties. So if you were to look at a periodic table, every single one of those are elements. Whereas a compound is a substance that contains two or more elements that are chemically bonded together. So if you were to take the H off of the periodic table and combine it with the O, or the oxygen from the periodic table, both of those individually are elements, but if you put them together, you can make water, which is a compound. Breaking down compounds, you could do this through a physical method to separate out mixtures, but you can't really use that to break apart compounds. You have to do something called a chemical change, which produces matter with a different composition than the original matter itself. So for example, heating is a process that's used to break down compounds into simpler substances. So here on the left, you have sugar that is on the stove. Once you heat it up, it's going to start to boil, and eventually that heat is going to be enough to break apart the bonds between it and create this black colored substance, and that is actually solid carbon, and water vapor is going to be released through the holes in that black substance. The same thing happens whenever you take a bite out of burnt toast. If you go just a little too long in the toaster, the color of the toast becomes black. That's actually the same thing that just happened on the stove. However, this is happening in your toaster. Heat is added for a period of time, and if it's too long, the sugars that are inside of bread will break down into solid carbon and make that bitter taste from your toast. Substances that are produced when when the sugar is broken down, it is essentially no chemical process that breaks carbon down into anything else. So when you are heating that sugar, there are many, many elements that are within it. Lots of carbons, lots of hydrogens, lots of oxygens. However, once you have used up and broken down all of that sugar, nothing can be done to break down the carbon that remains. There is nothing simpler than the element itself. So whenever you think of something like water, that could be broken down. Since water is also being released whenever this sugar is being heated, you could break that down. Now, it takes more than just heat to break down the the compound of water. You actually have to use electricity to break it down. After that is done, you can break it down into hydrogens and oxygens. Both of those you can find on the periodic table, meaning that they are elements, and meaning that all of your compounds have been broken into their smallest form. Elements cannot be broken down any further. There is nothing that produces something simpler than an element, unless you take apart the atom specifically. At that point, you would be removing protons and electrons, which would not happen. However, compounds can be broken down through chemical changes. Deciding whether a sample of matter is a substance or a mixture is based solely on the appearance can be very, very difficult. If you remember from one of our last screencasts, if you were to take a salad dressing, for instance, those are very homogeneous, meaning that you can only see one phase, or it all looks the same. This makes it very difficult to separate the individual things within that mixture. Therefore, you can try and do other reasons of deduction. You can look and see if there's more than one version. You can look and see if there's more than one phase, such as in milk. You can buy whole milk, low-fat milk, no-fat milk, light cream, heavy cream. All of these come from the same location, and since there are multiple versions of the exact same thing, you can conclude that milk and cream are definitely mixtures. You might infer that they are different amounts of fat based on their names and the different versions available. However, again, you can't be very certain about the composition without doing some chemical analysis. Whenever you're trying to distinguish a substance from a mixture, I like to use this little chart here. You start at the top, which is matter, meaning whatever you're looking at, and you're looking to see if it is a mixture of substances or if it is homogeneous, meaning you don't know if it's something together or if it is there's some other definite composition. So if you can separate it physically, you can look at the pure substance. It would be made up of the same thing. Or if it's a mixture, you have two types. It's either homogeneous, meaning you can't see anything other than the one phase or it all looks the same. Or it's heterogeneous, meaning it's non-uniform. Think of oil and water. There's going to be two phases there. If you can separate them, you get the substance, meaning it's going to be all the same type of thing. It's all homogeneous, but you could have a compound or an element. And you can determine which is which based on if you can chemically separate it. If it's a compound like sugar, you can chemically separate it into the elements carbon, hydrogen, and oxygen. So here's a quick way to apply if something is a mixture or a substance. This example, when a certain blue-green solid is heated, a colorless gas, and a black solid form. All three materials are substances. Is it possible to classify these substances as elements or compounds? So let's think about what we know about compounds. Compounds can be broken down by a chemical change, but an element cannot. So heating, remember about the sugar, can cause a chemical change. So that's important to remember. Now, if we apply this idea to the situation, we have the blue-green solid is heated. And remember, heating can cause a chemical change. So the colorless gas and the black solid appear, okay? And before heating, there is only one substance. So that means that the blue-green solid must be a compound, since we were able to break it down into two other compounds. However, since we don't know if the colorless gas was heated any further or the black solid was tried to be heated even more, we don't know if we can break those down anymore. So we're not sure if it's an element or if it's a compound. But for certain, the blue-green solid is a compound. The symbols that we're going to be talking about for the rest of the year come from the idea of the Swedish chemist, and I really wish I could say his name, but he uses the symbols of the Latin names of elements. That's why a lot of times whenever you look at them, they don't necessarily make sense. So each element is represented by either a 1 or 2 letter chemical symbol. The first letter is always capitalized. If there's a second letter that is used, it's going to be lowercase. So here are some examples. One that really doesn't make sense is sodium here. Its symbol, again, see that capital N, lowercase a. Sodium does not start with an M. However, its Latin name, natrium, is definitely starting with an N. So that's where sodium gets its name. There are other ones that do make sense, such as oxygen being O. However, not all of them match up with their Latin name. Chemical symbols allow us to get a shorthand way to write chemical formulas. Otherwise, we would be writing endless names over and over, and we'd never be able to finish a paper. We also tell you how many of these chemicals are in each compound using a subscript. Example of a molecular formula This one right here is glucose, also known as sugar. You can see that the chemical symbol for carbon, C, the chemical symbol for hydrogen, H, and the chemical symbol for oxygen, O. And the subscripts, the ones that are below the normal writing line, those tell you how many of each of these elements there are in this compound. So there are 6 carbons, 12 hydrogens, and 6 oxygens. And this applies to writing any formula throughout the remainder of this class. So all of these are able to be used, and we usually find them from the periodic table. We usually find the shorthand for these elements on the periodic table. So we actually are going to take a look at this further in class, but the periodic table has the elements arranged into groups based on how they react in a chemical reaction. So, for example, this portion right here, a lot of times will be used to make something taste really, really sour, whereas something on the right-hand side maybe we'll try and make something sweeter. So each element is identified by its symbol placed in the square. The elements are going to be listed from left to right based on atomic number. That's a good one to write down as a vocab word because the atomic number is unique to every element, and it is shown at the in the center above each one of these. So in this one, the number 11 is above Na, or sodium, and that is its atomic number. The atomic number also tells you how many protons, which are positive, and how many neutrons, which are neutral, there are within the atom. And we'll get more into that later. Each horizontal row, so horizontal goes from left to right, are called periods. There are 7 periods in the periodic table. 1, 2, 3, 4, 5, 6, 7. These guys down here are actually inserted into this portion of the periodic table, and we usually pull them out because it would make the periodic table extremely long otherwise. We call the vertical columns, so the ones that go up and down, we call those groups or families. And they're going to have very similar chemical and physical properties, so they're going to look very similar. So overall, we have these great vocab words at the end here if you can't remember. And we'll get back to different parts of chemical reactions in the next podcast.